Hi, welcome back to the Chem 4 review for the final. In this video we're doing example 1 to find the pH when you combine an acid and a base in the same solution. Remember, when you have an acid plus a base you end up with a salt plus water. That's the double replacement reaction, the 3 steps. Hopefully we'll get through this whole problem in one video. At the end, at equilibrium in the ICE chart, in the NICE chart, remember it's got to be in moles because it's neutralization. At the end, look to see which of these compounds, if they're there, will set the pH. If there's an H, you're going to use your pH equals formula. If there's an OH, that's a POH. If there's a salt and it contains a conjugate stronger than water, take that compound at the end of the NICE and turn it into the products. Remember, if you're doing that after the NICE, you have to change back to molarity. And then our new category, if you have at equilibrium after the NICE, if you're left with any weak compound plus its conjugate, that's our buffer, and we're going to use our Henderson-Hasselbalch equation. So let's look at our first problem. What is the pH of a solution that contains 30.00, well, let's make it 30.0 mLs of 0.120 molar HCl plus 30.0 mLs of 0.0300 m NaOH. Right away, you see that's an acid plus a base. That's going to give you a neutralization reaction where you get salt and water. Now remember, you have to be nice to the moles. So when you have a neutralization equation, your ICE chart's going to be in moles. Now they gave us molarity and volume. So to figure out number of moles of HCl, we're going to multiply molarity times volume in liters. Our molarity was 0.120. Our volume is 30 mLs. To change milliliters to liters, you move the decimal 1, 2, 3 places to the left. So our volume is going to be 0.0300 liters. So our moles of HCl comes out to be 9.00 times 10 to the minus 4 moles of HCl. For our moles of NaOH, again, M times V, our molarity is 0.0300. We're going to change milliliters to liters, 1, 2, 3. So again, we have 0.0300 liters. So our moles of NaOH works out to be 3.60 times 10 to the minus 3rd moles of NaOH. I'm going to write those values up here so I can erase this. 9.00 times 10 to the minus 4th moles of HCl and 3.60 times 10 to the minus 3rd moles of our base, NaOH. So I think we're all ready for our NICE chart. So the first thing is we're going to write a balanced equation. Remember, this is a double replacement. Fortunately, this example is very simple. You probably even have it memorized without even realizing it. Step 1, switch the anions. So our products are going to be HOH, which we expect, and we expect to get a salt from an acid and a base, and that's when we combine Na and Cl. Now step 2, you'll remember, for double replacements is to check the oxidation numbers on the salt to make sure they add up to equal 0. If they don't, we crisscross them. But in this case, +1 and -1 add up to equal 0, so we're all set. Step 3 for a double replacement, do you have the same number of atoms on both sides? And we do. 1 H, 2 H's, 1 Cl, 1 Na. We're all set. All right. So we have our balanced equation. Let's do our nice chart. Remember, anytime you have an equilibrium chart, well, let's just go ahead. Our initial concentration, not concentration, moles, we figured out for HCl 9.00 times 10 to the minus 9 moles. And for NaOH, 3.60 times 10 to the minus 3. Remember, unless the problem gives you concentration of product at the start, you assume that the reaction hasn't started initially, I, so you're going to write in zeros. Now something that's a little bit different, another thing that's different besides the moles for a nice equation, is normally we would subtract the x's here and add the x's there. But when you have a nice chart, you don't subtract x for change. You subtract the limiting reagent. Which of these two is smaller? That's the limiting reagent. And in this problem, a number times 10 to the minus 9 is our limiting reagent.
Oh, I just got a yellow.
A yellow?
Mm-hmm.
What does that mean?
I don't know, but it happened the last time. Maybe it's getting close.
Battery?
No, maybe memory's getting full.
Oh.
It's okay.
All right, so when we subtract this, wait a minute, did I write it backwards? Did I write these numbers backwards? I guess I wrote these back. 3.60 moles of HCl, 9.0 times 10 to the minus 4th NaOH. Somewhere along the line I switched them. So 3.00, I'm going to write it out as a decimal so it's easier to see. 0.00360 moles here, 0.0009 moles here, and so our limiting reagent is the smaller number. We're going to subtract 0.0009 from both of these. We end up with 0 moles of NaOH, and we end up with 0.00270 moles of HCl. Now here we're going to add the limiting reagent. And we end up with 0.0009, 0.0009. Now this is where it gets tricky. You have to look with what you're left with and decide which of these is going to have the most impact. Now we're left with a strong acid here. We're left with the conjugate that's stronger than water. And we're left with water. Which of these do you think is going to impact the pH the most? Of course it's going to be the strong acid. Because a strong acid, H plus or a strong base, is always going to affect pH more than a buffer. Time. And we're going to finish this on the next video. Bye-bye.